Hi, my name is Brianna Morales. I'm currently a freshman at UCI and I'm majoring in chemistry. And today I will be teaching you about the activity coefficient. So the activity coefficient is going to be represented by gamma, and it's going to equal the activity of series I divided by the ideal concentration or partial pressure of series I. You would use concentration when dealing with aqueous solutions and then partial pressure when dealing with gases. So the importance of the activity coefficient is that it measures the effectiveness of a value. And what I mean by that is that it measures the deviation from ideal behavior. And this is super, super important because, we're mathematically applying chemical concepts or chemical theories. We're not taking into account that there is non-ideal behavior going on by molecules in reality. So this activity coefficient compensates for non-ideal behavior in the real chemical world that we don't see in chemical concepts or theories. And as we all know by now, these chemical concepts and theories are mostly right and they have a lot of truth to them, but they don't account for what is realistically happening. And so this activity coefficient provides a more precise calculated number of any value because it is the fractional difference between an ideal value and a non-ideal value. And of course, the non-ideal value is going to be more precise because it represents a number, it represents a value that is related to what's realistically happening. And so before I continue on, I'm going to touch up on my sources. So of course, I used to test the textbook. I learned about the activity coefficient and several chemical concepts like calculating the equilibrium constant K and van der Waals equation and Raoult's law, etc. And then I used the chemical website library text to learn about the derivation of the activity coefficient, and it helped inspire my own example that I use in this presentation. And then I watched this lecture by Dr. Jay Ratliff from Limestone College, and he talks about the activity coefficient, and I learned the basis of this whole concept from him. All right, so the activity coefficient in M2C, because of what we have recently learned about activities in this class, I will be talking about the activity coefficient when calculating the equilibrium constant. All right, so for simplicity purposes, I will be referring to this equation on this slide. And so, as I hope we all know by now, to calculate the equilibrium constant, we're going to take the activity of the products multiplied by each other, divided by the activity of the reactants multiplied by each other. And so what you see here is you're seeing this first equation rearranged and plugged in. So as you see here, for each chemical, we're going to have its concentration multiplied by its activity coefficient. So in this case, I'm just using the concentrations. We're assuming this is a solution, an aqueous solution. But for gases, you would use the partial pressures, but the same rules apply and the same approximations apply. So to obtain the concentrations mathematically, you would divide moles of solvent by liters of solution. And then to obtain the activity coefficient, to then calculate K, you would just look at a table containing these numbers because the equation used to calculate these numbers, the Debbie-Huckel equation, is way too complex, and it is for a higher level understanding of chemistry. So the derivation of the activity coefficient equation. So first and foremost, the activity of any pure solid or liquid is 1. And that is because the concentration of a pure solid or liquid at equilibrium is equal to its concentration at a standard state. And as you see here, that is how you calculate activity. Same thing for partial pressures, as I said before. And that is why we don't include the activity of any pure solid or liquid in the equation when calculating K. As you see here, we have a chemical reaction with the pure liquid water, and I'm not including its activity here. And for the sake of simplicity of typing in Word, I just use A, B, C, and D, so I hope you get this reference right here. And so I'm not including it in this equation, so I have the activities of all the products and then just NH3 plus here. And then I'm gonna rearrange the first equation that I showed you guys and plug it in like you see here. And then I'm just gonna separate them. I'm gonna have the fraction of the concentrations here and the fraction of the activity coefficients. And so because this is a dilute solution in this chemical reaction, we're going to assume that this fraction of activity coefficients is close to 1. And because we're going to assume that, we're just going to take it out. We're just going to like throw it away, because you can do that. And we're just going to be left with the fraction and the concentrations. And so that is what makes the law of mass action equation, is taking away that fraction of activity coefficients. And that is why there's a difference between calculating K with activities and calculating K only using concentrations. That activity coefficient makes a difference. How big of the difference just depends, but no matter the difference, it will just be different. And so a higher activity coefficient means there are more repulsive intermolecular forces, and then a lower activity coefficient means there are more attractive intermolecular forces between solvent particles. So that is really going to be, so the intermolecular forces is what determines the magnitude of difference between calculating the equilibrium constant using only activities and then calculating K using only concentrations. And so we'll get more into that with this example. All right, so right here we have this chemical reaction, the decomposition of barium sulfate in a saturated solution, and it reaches equilibrium. So we have the K for this reaction is 1.1 times 10 to the negative 10 power, and then we have barium 2 plus, and then sulfate have activity coefficients of 0.38 and 0.355 respectively. What are their concentrations at equilibrium? So I calculated with activity coefficient and without activity coefficient to show you the difference between the two. And so here we have K equals the activities of barium 2 plus times the activity of sulfate divided by the activity of barium sulfate. And like I said before, if it's a pure solid or liquid, the activity is going to equal 1. So this equals 1, we don't include it. So I rearranged the equation, substituted the first equation that I showed you guys, and then we're stuck with this, the concentration of barium 2 plus times its activity coefficient, and then the concentration of sulfate times its activity coefficient. And so we plug in the numbers now. We have K right here is equal to the activity coefficients. And then here I just put x squared because these solutions are going to be the same because we start off with 0 of each. And so we solve for x, and we get a value of 2.9 times 10 to the negative 5. So barium 2 plus, my bad, and then sulfate both have this concentration. Okay, so now I calculated without the activity coefficient. So we do the same thing here. We solve for x, and then we're going to get a value of 1.04 times 10 to the negative 5. And that's a pretty big difference. That's a 36.7% difference. And so if you guys remember, when it's a diluted solution, this fraction right here is going to be close to 1. So we could throw it out and there probably won't be much of a difference. But because we have a saturated solution, we see that difference here. So this would be an ideal calculation right here, and this would compensate for the non-ideal behavior here. As you can see here, the activity coefficient is less than 1, and we have a low activity coefficient. So that means in reality, there are more attractive forces between the solvent particles. So we're going to have a higher concentration. All right, so in conclusion, using the activity coefficient allows for the effects of intermolecular forces to be compensated for, and it provides more precise calculations. And the activity coefficient can be really useful because you can apply it in almost, I don't want to say everything, but a lot of equations in chemistry, and you can use it to calculate almost any deviation from non-ideal behavior. And so you should use it when the behavior in a chemical environment is more non-ideal, because when it's closer to an ideal, when the molecules are behaving more ideal, then there's a need for it, but not as much of a need, if that makes sense. So that is all for today. I hope you guys enjoyed this presentation and have a good one.